Okay, this will complete what we did in class to make sure that we have all the steps written down, how to solve these first series of problems in Newton's laws. So, using the same schematic that we did in class, we're going to be focused around the five-step method. If you need a refresher on the five-step method, I refer you to the video that isolates just the five-step method and all the kinds of ins and outs about it. But for now, let's try to tackle this problem just like we did in class. Okay, so the first step, as always, is to draw the free body diagram. Okay, and so I'm going to draw the free body diagram, which again, if you remember, is simply a sketch of the object in motion in question, which for us here is going to be player B. And we draw all of the appropriate forces acting on that body in their respective directions. And so, as we discussed in class, we have the force of gravity, or the weight, pulling down, the applied force from player A pulling to the right, and we have the normal force going up. Okay? We then go to step 2, which is to simply write out Newton's laws in totality. Again, even if we don't use both directions for a particular problem, this is our autopilot step where we get in the habit of writing them down. Once we have them written down, that's when our free body diagram becomes the most important thing. And so we take the forces in the x and apply them to the x direction. We take the forces in the y and apply them to the y direction. So that means our two red equations now become the blue equations, where we have the applied force with a positive sign because it's pointing to the right is equal to the mass times the acceleration in the right. And just for completion's sake, we should be clear that this is not the mass of A, but the mass of B. And for the y direction, we have the normal force going up, so it gets a positive sign. The force of gravity coming down, so it gets a negative sign. Okay. In this video, what we're really setting out to do is to finish off in detail all the problems that we did in class, and then to make sure that we have a little bit more practice using Newton's laws, and in particular the five-step process that we talked about. If you need more help on the specifics of the five-step process, I refer you to the video which explains each one of the steps in detail. So let's jump right in. We know that in the five-step process, if we're going to solve the problem from class, which is right here, the first thing that we need to do is draw the free body diagram. And remember, the free body diagram is a simple sketch of the object in question with all the forces on it labeled and in their proper directions. So we know we have the applied force from player A going to the right, acting on player B. We have the force of gravity of that player being pulled down, which is also known as the weight. And we have the contact force, or normal force, going up. Okay, now that we have the free body diagram, we're free to go to step 2, which is our autopilot step, which just says that even if we're not going to use it, we write out Newton's laws for both directions. And it's going to become very clear very quickly in the next couple of lectures that we're going to always eventually need both directions, even if it might not seem so at first cause. Okay, now that we have this, we can then plug in the forces from the free body diagram into the left-hand side of Newton's second law, and we can execute step number 3. So plugging these in for step 3, we see that in the x direction we only have one force, which is the applied force, and it's going to the right, so it's positive. So we get Fa is equal to the mass in question, which again, remember, is mass B here, times the acceleration in the x. And then for the y direction, we have two forces. Normal force is going up, so it gets a positive. Force of gravity is coming down, so it gets a negative. And that's mass of B times the acceleration in the y direction. Next comes plug in the physics. So here, what are the extra physics that we know? Well, first and foremost, we know the formula for the force of gravity is just the weight, which is the mass times the acceleration due to gravity. But we also know something about the acceleration in the y direction, namely that the player is neither jumping off of the ice because of the force applied from player A, nor is he tunneling through the ice. So what we're really saying is that the acceleration in the y direction has to be 0. If we take those and plug them back in, then we just simply get a rewrite of the first equation, and then we get a nice compact equation for the y direction. We're now ready to do step 5, which is to solve for the desired quantity. The desired quantity in this case is the acceleration in the x direction, and so that's the one that we're going to solve for. And we see simply that the acceleration in the x direction upon dividing by the mass is the applied force divided by the mass of the player. We can then take those numbers as is and plug them in. Upon doing so, we see that the acceleration that we get here is a small one because they did start from rest, but it's 0.1 meter per second squared. Okay, after we did that, we then elaborated a little bit and said, well, what if we have a little bit more to the story here? We just said that the acceleration in the x direction is 0.1 meter per second squared. But what do we know about that? We know that that number is a constant. And if the acceleration is constant, that allows us to use our good old friends from the previous chapter, namely the kinematics equations. So, what's the particular kinematic equation in question here? Well, we know the initial velocity was 0. We have a time. So this is a perfect candidate to use equation 3, which said that v final is equal to v initial plus at. Here we have that the time is equal to 2 seconds. We have that the initial velocity is 0, and we want the final velocity, so we can now plug this in, which is going to be v final is simply the acceleration times the time, which is 0.1 meter per second squared times 2 seconds. One of the time units cancels, and we see that 0.1 times 2 is going to just be 0.2 meters per second. Lastly, if exactly at the 2 second mark player A lets go of the stick, how fast will player B be traveling after? That was supposed to be a 6 there, but it looks like it didn't carry over from the slide. But we know that we can simply here apply Newton's first law. That after 2 seconds, if you let go, there's no forces acting on it, so an object in motion will remain in that motion unless acted upon by the external force. The ice is frictionless, so there's no force there. So what was the motion at the 2 second mark? The motion was a velocity of 0.2 meters per second. So then we know that at any time, the v final at 2 is going to be the same at v final at 6. It's going to be the same as v final at any time, which is going to be just 0.2 meters per second until an external force. And the world is a happy place. So let's go to the second problem that we did as a challenge to the class and make sure that we all know how to solve this moving forward. So we're going to see that the procedure is very similar. All of these problems in Newton's laws are all going to be the same type of procedure. So let's just go for it. We start with number 1 and we draw the free body diagram. So again, we have a person who is being pulled to the right by some applied force. Their weight is coming down and the normal force is going up. We then go into our autopilot step and we say that the sum of the forces in the x direction is equal to the mass times the acceleration in the x, and the sum of the forces in the y is mass times acceleration in the y. We then jump in and we can now apply the forces from our free body diagram so that our first equation just becomes a rewrite with the applied force is equal to the mass, and let's just be clear here, okay, that this is, we're talking about the mass of the partner times the acceleration in the x direction. And for the y direction, we get the normal force minus the weight of the partner is equal to the mass of the partner times the acceleration in the y. Now we go to step 4, and we can apply the physics that we know. This partner is not flying off the ice, nor are they tunneling through it, so the acceleration in the y is 0. And the force of gravity for this partner is going to be the weight, which is mass of partner times g. And so we can now plug these into the appropriate equations, and we see that this one becomes just a rewrite, and the next one, much like the problem we did earlier, gives us a very similar looking equation. Now we can solve for the desired quantity. The desired quantity in this case happens to be the mass of the partner. But in this case, we know the applied force and we know the acceleration that is resulting, so we can now divide both sides by the acceleration, and we see that the mass of the partner is going to be the applied force divided by the acceleration in the x direction, which upon applying these numbers is going to be 40 newtons divided by 0.8 meters per second squared, which comes out to be 50 kilograms. Okay, so if we then go to the bonus segment, she then performs a lift on her partner and holds him stationary over her head. With what force must she exert to hold him up? Well, we're going to need a new free body diagram for this, aren't we? Well, if we do the new free body diagram, right, upon the lift you have for the mass in question, which again is still just the partner, you now have a different looking free body diagram in the sense that he is getting a force up from her arms, which is now the applied force, but his weight is still pulling down. We no longer have a force in the x direction, so we go to our step 2, which says write it all out. We go to our step 3, which replaces everything in the left-hand side, which for the x direction gives us 0 is equal to mass times acceleration. Nothing wrong with that, a nice easy one. But in the y direction, we have the applied force going up minus the force of gravity coming down is equal to the mass times the acceleration in the y. We now apply the physics. Well, if you're holding the person up stationary, what does stationary mean? Stationary means that there is no motion. So that implies that the acceleration in the x is the same as the acceleration in the y, which has to be 0, which, by the way, we've already figured out from this equation here. But let's now plug in that acceleration in the y direction being 0, and of course the fact that the force of gravity of this person is the mass of the partner times g. And so then this equation becomes the applied force needed minus mpg is equal to 0. And we can now solve for the desired quantity, which in this case is the applied force. Therefore, the applied force is equal to the mass of the partner times the acceleration due to gravity. We found out the mass of the partner earlier was 50 kilograms. So this is 50 kilograms times 9.8 meters per second squared, which gives us just shy of 500 newtons. So it will take more of a force, obviously, to lift this person than to drag the person in the manner that we did in the previous part of the problem. For the bonus squared, we can simply just, I'm going to slide this all over here. For the bonus squared, we can simply use the fact that we know that when the dance began, she was pulling to the right with an acceleration, with a force of 40 newtons. Okay, we now know the mass of the partner, we know the acceleration that she was pulling at, and we know that 3 seconds later, the lift takes place, which means that's when the acceleration in the x turns off. Therefore, all that we need to do is know that the acceleration in the x direction was 0.8 meters per second squared. This number is a constant. And since it's a constant, it means that we can use our good old kinematics equations. We started from rest, so we have a v initial of 0. We have a time, which is equal to 3 seconds. And so this is a perfect candidate, once again, for good old equation 3 from our previous chapters, which tells us that v final is equal to v initial plus at, which means that v final is just at. And so we see here that v final is simply 2.4 meters per second I hope that this provided some more context and some more detail. We're going to be spending the next couple of days going over lots more problems like this. So, as always, if there's any questions, please come to class equipped and armed with them. And until then, never stop thinking.